right, thanks. And Katie really wanted to come, but she's in a wedding tomorrow, so this was the only day she couldn't make it. So of course her guy got scheduled here, so I'm filling in. Just along the last two talks, we pretty much had the same ideas, I think. Can habitable brines occur on Mars today? And I believe you already know the answer to that. So before you can have a brine, you got to have salt. And so everyone's excited about these perchlorate salts. They're at every landing site. They allow to these very cold temperatures, and they can absorb water right out of the atmosphere. Just as we've been seeing in this picture, we think we might have actually seen this at the Phoenix landing site. So how do we calculate how much and when brine forms from a salt? So we use these phase diagrams, as everyone's explained before. So this was the phase diagram I was used to using before Katie and I started working together. This is more the melting one that Herman talked about, where you have the weight concentration of the salt going down, and you've got different phases where you'd have liquid and liquid plus ice and different things. And then when Katie started working with me, we started using this relative humidity, water activity versus temperature, and how these two combine is very interesting. So here's your DRH again. So as you increase, so we're using Katie's favorite salt here. Sorry, this is magnesium perchlorate instead of the previous ones, which were calcium perchlorate. So as you increase your relative humidity, you get liquid, and then you get this efflorescence relative humidity over here, which for magnesium perchlorate is not temperature dependent, while the DRH actually is. And so what we've been trying to do is actually combine these two models to figure out what's going to happen in the subsurface. So if you actually had that perchlorate down there and it starts absorbing water, it's going to start moving to have a lower and lower weight concentration. And we're also trying to look at the kinetics of this in the lab, which is not going to be presented today, but we'll at another time. So this is just another way of looking at this phase diagram. So this is just showing how much volume of brine that we have. So if you're in this area, you have 100%. If you're mixed in these other two areas, and then if you're out of the brine zone, you have hydrate instead. And then so what we can do there is then look at the water activity based on these same parameters in this phase diagram, and then we do the same thing. So we were actually using the COSPAR definitions just because they were a little more liberal. They were going all the way up to 0.5 water activities and any temperature greater than 248 K, just to try to get some sort of habitability in here. And then just going back, what we did is we just used this water activity that's right here, and then just kind of went with what the volume percent is, and that way we can actually make this deliquescence phase diagram kind of the same way. And so here, it's just showing the same thing that the model works. This is just kind of numerical errors in here, but this is the model that we're going to be using to figure out how long this brine is actually stable anywhere in the subsurface. So we're using this model. We have to pick a place on Mars to use it. So naturally, let's just pick Palikir Crater because it's got a ton of significant RSL activity. I'm kind of an RSL guy. And Chrism might have found perchlorate here. Others would disagree with that. So what we did was we used Mars flow modeling. And while we're trying to get deliquescence and efflorescence to happen in Mars flow, it's not quite there yet. So we had to do some post-processing on that. So Mars flow right now is the version we're using is this 3-phase simulator for water migration in partially frozen media. It does not do salts. So if there were any phase changes, they happen at pure water, like at 273 K. And what we're outputting here, among other things, is temperature, RH, versus time. And the time interval that we save at is this 10 minutes. We do a 1D model on west-facing slopes at 30 degrees because we're trying to get at where these RSL are occurring at Palikir Crater here. We have 24 different layers into the subsurface from 0 to 10 centimeters. And then in that, we have different geologic zones where we have like a silty dry unit on top, a sandy dry unit, and then a bedrock that would be saturated with ice below that, which provides a lot of water vapor there. And then afterwards, after we output all this, then we go into this post-processing where we use the deliquescence and efflorescence to actually calculate how much brine would actually be there. And so by doing this and not having it all coupled, We're not accounting for any latent heat effects when you actually form this liquid. There's no changes in thermal conductivity when you have a brine compared to just a dry salt, and there's really no vapor diffusion either. Just going towards temperature. So this is a bit complicated. So this is seasonality. This is solar longitude up here, where we start at 10. So we're just moving over the entire season. And then this is the temperature, and then this is going to be the maximum temperature at every sol and the minimum temperature at every sol. So they're color-coded. The legend is kind of over here, with 0 being at the surface, and then this blue being our deepest layer at 9.5 centimeters. And so you can see as you go down, you get less temperature variation. At the surface, you get a lot of temperature variation. And so clearly, there's no way we're going to have brines in the wintertime, because our maximum temperatures aren't even getting above the eutectic, which is what we need for brine formation. So now we're going to look at relative humidity versus seasonality as well. And so this DRH, we actually have 2 lines here representing the DRH, because at colder temperatures, it's going to be around this value, and at warmer temperature, it goes lower. So during the wintertime, we have a very high DRH, and this is because it's colder on Mars. There's a lot of ice in this system with this icy bedrock, and so that's actually keeping the relative humidity high during the wintertime. But then during the summertime, we get very low relative humidities, and you can see this distinct jump that happens right here. And so what actually happens here is in the wintertime, when we look at this data in a different way, we can actually see all sorts of cold trapping that's happening in these upper surface layers during the wintertime. So we're getting ice forming in there. And then right around this Elsevest right here, at the surface, all of that ice that had been trapped during the winter goes away. It sublimates away. And so now we're dropping to these very, very low minimum humidities. And then just lastly, to say on this slide is that, obviously during the summertime, when we would have RSL, it's definitely going to be too dry for any magnesium perchlorate brines to form, because this RH is never going to get to the DRH. And then just to make this plot very complicated, I'm just going to add 3 more of these layers in. And just kind of why I'm showing this, taking the risk of showing this, is just it's interesting to see where that cold trapping, that ice goes away. So as you get deeper and deeper, you can hold on to that cold trapped ice a little bit longer every year, but then that goes away. And then you can also see these little blips right here, which we're, what the heck are these? And this is actually where you get a little bit of cold trapping, even after the summer peak has occurred. And so this will have a little bit of a cold trap, a little bit of ice, which will increase the relative humidity there in the subsurface. And then the next day it will sublimate away, and you'll go back down to kind of the trend there. So then what we did, just kind of like what Ed and Vince had been talking about before, is we were looking at combining the temperature and the relative humidity, just to see where we would actually get into that DRH range, where we'd actually have brine. And then if it was brine, then we looked to see when it would go away, and that we'd use the ERH for that. So we had that kind of metastability in here. And so you can see that, I'm doing it too. All right. So at the very deep unit here, so I'm just showing the bottom unit and the top unit. At the bottom unit where we have ice, and then we also put perchlorate in there, you're going to have brines all the time, anytime it's above the eutectic temperature. So this is just a melting effect. This is where the brines are going to be between the ice grains, triple junction effects, things like that. And then at the surface, you're going to be way too cold during the wintertime, and you're going to be too dry during the summertime. But in these transition phases, in the spring and the summer, you're actually going to have enough humidity and temperature to actually have brines there for a significant part of the day, again. And then just to complicate things, showing everything else, I'm just showing this because at this like 5.1 centimeters, you can actually have brine there for an entire sol, again. And even up to 3 centimeters, there are times where you get enough cold trapping occurring, and that hasn't sublimated, gone away yet, that you could actually have brine there for a very long period of time. And then just instead of showing the none plot like Vince did, the brine is never habitable, even according to these COSPAR guidelines. So deadlines. Yeah. So the water activity is never greater than 0.5, and if it was greater than 0.5, then the temperature is never greater than 248. Yeah. So so we can try different places, trying different obliquities too, and then just to kind of show what's happening on a diurnal scale, we're going to look right here at 206 K. And so that's what's shown here. So again, for Palikir Crater at 206, and instead of being at the surface, we're going to be right under the surface, so at half a millimeter, just to have pores in there instead of just degassing out to the atmosphere. So this is our temperature. It's going to be on the left plot, and then this is going to be our relative humidity or water activity that's going to be shown here on the right. And then we just show the eutectic temperature on there, the ERH, the DRH was just temperature dependent again. And then what we do is this post-processing that we're doing. We're taking this initial RH or water activity, and then we're going to decrease it to the DRH. So if it's above this, it should be deliquescing out. So it's going to be pulling water out of the atmosphere, and we're going to add that to the condensed phase, how much is in that condensed phase. And then likewise, we're going to do the same when it gets below the ERH. So if it's too low in humidity, we're going to take that condensed phase out and actually sublimate it away so it provides a more humid environment. And when we do that, we can calculate the volume of different mixtures that we get. So when it's below when it's below the eutectic temperature, like before like 9 a.m. here, we're not going to have any brines. But then after that, we can actually start having brines, and these brines are going to exist even through where the ERH is. And so I'll explain that more kind of in the conclusions here, but first the assumptions. So to get these volumes, we needed to assume how much H2O was there and how much perchlorate was there. And so we just used these assumptions. This is just based on the neutron data at Palikir Crater, and this is based on Phoenix. And so just to conclude here is that these brines are not going to be habitable, even though it looks like they can form under this situation that we showed, which is very favorable. Temperature seems to dominate here. So we have a lot of brines occurring in here, and this is just really as the temperature increases, more of this ice starts melting away, and it is able to form the brine. And then even through efflorescence, when we're below efflorescence would predict, we can actually sublimate or evaporate enough of that condensed material to increase the relative humidity here and keep that brine stable there. Now, we need to do better modeling with this to figure out, so this isn't a pore, so that, it's eventually going to vapor diffuse out. But we're going to do that modeling next. And so that's part of this future work where we're looking at, in the laboratory with macroscopic, more deliquescence type measurements to really look at the kinetics that are going on. And then we're trying hard every day, trying to get this Mars flow salt model to work where we can actually add salt and do all this all in one model. So we'll be presenting that at a poster at 9th Mars under Katie's. Katie will lead that. So with that, I'd take any questions. Thanks.
We have time just for one quick question.
Okay, it's more of a comment. Andy Sugar from the University of Florida. I've just finished, I've got a Mars chamber in my lab, a real highly capable system. And I've just completed a series of experiments where I've taken rocks of different geochemical composition and figured out a way to put frost layers on it up to a centimeter thick. And then heating that up by either turning on the UV visible and near infrared illumination system or heating from below. And the classic Haberle et al. Paper in 2001 predicted this really tight window around the triple point of water of liquid, triple point for water on Mars. And I can see clearly pure water flowing off the ice and into the rock and hydrating the rock, not a salty brine at a depressed temperature, but liquid water flowing off the rock at 7 millibars in a Mars atmosphere between 0 and 4 degrees centigrade. So this has been really interesting the last two talks, but I would say that where that niche that you may not have considered yet would be underneath frost layers at the places where that might occur. It might not be something that happens generically out on the open terrain as you're cycling through diurnal temperature swings, but there could be a habitable zone underneath or at the margins of ice. So,
okay, thanks.